Hey everybody, we are back in chapter 3. We're here to talk about functions today. A function, very simply, is a mathematical thing that turns one set of values into another set of values. And honestly, we've already been doing this. Okay, there's no magic here or anything. Let me show you what I mean by that. Before, we might have written y equals 2x plus 3. And you knew that we could take values of x and put them in the top of that thing, and we'd get y values out, right? Well, this is the same thing, all right? The notation is going to be a little bit different, but it's the same ideas. We're putting values in, getting different values out. There's this big, long, complicated definition here. If a variable y is so related to variable x that whenever a numerical value is assigned to x, there's a rule according to which a unique function of y is determined, then y is said to be a function of the independent variable x. Okay, and that's what we were just talking about. You're going to put x values in right here. You're going to get y values out right there. Got some pictures down here at the bottom. If I take some number, and maybe it's a 4 or 7 or whatever, -2, uh, let's just call it p. It could be any number. I put p in, and it says, all right, I'm going to turn that into an m, right? So that number p came in here. We turned the crank, it went through the machine, and ding, it dropped out another number, which might be called m, there. All right. That's what the function does. If we take q and get n out, that's fine. We could also take r and get n out. That's okay if you get the same thing out. But over here, like you see, if you put one thing in, you better not get two things out. All right. If I put the number 3 or 6 or whatever in here, let's put 6. If I go 2 times 6 plus 3, there's only one number that can come out of this, right? 15. And so there is a unique value of y that comes out. And every time I, put whatever in and I get a number here, that is unique to whatever I put in. I don't want this. Q cannot turn into Y and Z. Q can turn into Y, R can turn into Z, Q can turn into N, R can also turn into N. That's fine, but I can't have one thing that I'm starting with mapping over here to whatever it ends up in. That's no good. All right. That is not a function. And that's the main thing that you need to know about functions. You put one number in, you only get one number out. All right. And it's there's not two or three or more that come out of that thing. Here's a picture version of that. Sometimes we call this the vertical line test. And what they're doing is they're saying for any function, and I could graph that function here. Let's say we put in x equals -2 right there and see how I come up, and there's only one value right there. The idea with the vertical line test is if I draw a straight line all the way down through that, not very straight, is it? Then I only hit the graph in one point, and I can do that as many times as I want. If it passes the vertical line test, uh, then that means that I've got myself a function. All right. Over here, when I drop a vertical line down, I'm hitting in two places. So that failed the vertical line test. I put one number in. What is that? X equals 1, 2, 3, 4, 5. Okay. X equals 5. And on this right here, I'd be getting, I don't know what that is, Y equals 3.3 and 1, 2, and about -2.5. Okay. I can't get two numbers out and still call it a function. I can have a mathematical arrangement that does this. But in effect, it'd be something like x equals y squared, and maybe a little number here and up or down a little bit, or something. I've got a thing that does that, but it is not a function. And we'll put FCN for function, just kind of as an abbreviation, right? You can see this thing fails the vertical line test everywhere that you put it. Okay. So that's not a function either. But this guy over here, he passes the vertical line test. You put one number in, you get one number out, and that's it. Function. That's good. All right. Um, there's some notation here that we use when we're talking about functions, and some people have a hard time with this word function. And it's like, what is a function? Well, a function has a function, right? It does something. And so that's the way I like to think about it, that a function does something, and you say, well, what does it do? And I say, well, it turns these numbers into those other numbers, right? But it has a function. And the notation that we're going to use, and really the only change we're making here, is instead of writing y equals 3x plus 7, we're going to get rid of this y and just call it f of x, some function of x, could be g of x, h of x. We're just giving it a name to say this is the machine that turns x values into the function values. We have some terms that we use for that. The numbers that we put in are referred to elements of the domain. They come from the domain. The numbers that we get out, we refer to as the range. So here we're putting in elements of the domain into X, and the numbers, the range comes out over here as f of X. Maybe I should draw it down here. Um, domain in, range out. I don't know who came up with these names. I don't know why they came up with those names. It's just what we call it, right? But I would read this right here, this whole thing. I would say y is a function of X. Okay. You could have a function of more than one variable. I could have a different function, which might be the function z, and it's a function of x and g and r. Whatever variables I'm using here um, to do this, but that's what the stuff in the parentheses there says. These are the variables involved in this rule, in this relationship between variables. They're all listed there to where I know what variables I need so that I can plug them in and get an answer. Here's an example of that. Here they give us a function right here, and then they say they want us to evaluate, and that's the word. It says plug it in and see what you get. Plug it in and simplify. Okay, so nothing, we've been doing this the whole time, right? Um, they want me to take this value of -4 and put it in everywhere that I see p. So here I'd have -4 squared plus 2 times -4, and -4 squared is 16. Remember your order of operations here. And a -8, 6 plus -8 would be a +8. Okay, so we just took h of -4, and that is equal to 8. And then I could put a in there. All right, so this would be a little bit different one. But if I write a everywhere I see a p, then I'd have a squared plus 2 times a. All right, and that would be h of a. So sometimes it's good to think, be able to just drop a new variable in there and think abstractly about it. Sometimes you want to plug a number in, just whatever they have, just replace all the p's with whatever's inside the parentheses, and you're done. This one on the bottom says, here's a different one. This is a function called g, and you can literally call it anything you want. It's just a name for it, right? But if g of m of some variable equals the square root of m minus 4, then they want us to take this 5 and plug it in everywhere that we see an m. So that would be equal to the square root of 5 minus 4. 5 minus 4 is 1, and the square root of 1 is 1. Okay? So there's nothing really surprising there. The notation's a little bit different, but there's a reason for it. And we're talking about this as a function instead of, y equals 3x plus 7 or whatever. But other than that, it's the same old thing. We can go the other way here. In this case, They gave us a function, and now they're saying, now you've got the value of the function, so go get x, solve it for x. So I can kind of do the same thing. I can take this 4 and I say, well, f of x is 4, so let's just replace it, and I get that. And now they want me to solve for x, and I go, okay, I've done that. Ooh, x squared and x and a constant. That looks like a quadratic. Let's get everything on the one side or the other so that there's a 0 on the other side. And then we'll be able to maybe factor it, maybe complete the square, maybe quadratic formula. Let's see where it goes. X squared minus 3x. I have to subtract 4 from both sides. This is going to be a negative 4. And I would try factoring it first. This looks promising. My factors of 4 are 1 and 3. I'm sorry, 1 and 4, which would add or subtract to 3. The 2 are 2 times 2 here. I'm not going to get a 3 out of that. So let's try with that 1 and 4 thing. X times x would give me the x squared. If we're doing 4 and 1, the signs are different. And I need the big one to come out negative. Then I'd have a negative 4 and a plus 1. Let's check it out. X times x is x squared. There's a 1x minus 4x would indeed be negative 3x from the outer and the inner. And the last times the last is definitely going to be negative 4. So that's my factorization. And you know what to do with this. You take it apart. I'm multiplying two things, getting 0. So either x equals 4 or x equals negative 1. And we've done those, so I won't belabor the point, but that's a possibility too. Maybe they give us the value of the function, we put that back in and find the variable that would crank that number out for us. And here you can see there are two. When we talked about quadratics before, we saw that a quadratic had a possibility of crossing the x-axis in two places. So we would fully expect to see that function that's in the box there look something like that. That's pretty poor representation of it, but you get the idea. Okay. Here is a relationship. It's not necessarily a function yet. They want us to write it as a function. And so the first thing that we would do is solve it for r in terms of t. So r is a function of t. If I take that thing 3r plus 2t equals 18, and I want to get that r out there by itself, well, then I'd subtract 2t. Maybe you want to flip that around. Maybe you don't care. I don't know. Divide by 3, though, is definitely in there somewhere. Okay. And that would be my function. Right here, I've got it written r equals 18 minus 2t over 3. So that would kind of be that equation or relationship or formula or whatever you want to call that. And if I want to put it in this functional notation where r is a function of t, then I could come in here and just replace the r with f of t equals 18 minus 2t over 3. You can see that that's a function, and you can see that the only variable, the complete list of variables in the function, all I need to do is know the value of t, and then I can go evaluate the function of the, evaluate the, get the value of the function. How about that? Okay. Now that we have it as a function, I could definitely come in here and they could say, give me what you get when you put negative 3 in there, right? And so I'd come in here and say f of negative 3 equals 18 minus 2 times t, but wait, t is negative 3, so I'd look like that, and I'd get busy and simplify that. Negative 2 times negative 3 is positive 6, and I add that to 18 and get a 24, and I still have to divide by 3, so that's going to be an 8. All right. Maybe on the other hand, They do the other way where instead of evaluating, I'm solving. So now they're saying the function's value is 2. And let's write that function again here so that we can see it. F of t equals 18 minus 2t divided by 3. They're saying this f of t is actually 2, so I'm going to scribble this out. Put a 2 right there. Maybe you want to drop down to the next line. That might be a little nicer. But now I'm trying to get t by itself. So I could come in here, multiply both sides by 3. That would cancel on the right, give me a 6 on the left, equals 18 minus 2t. I don't think there's a whole lot of surprises here. We'll subtract 18 from both sides. And that would be 6 minus 18 is a negative 12. That's equal to negative 2. And now we need to divide by the negative 2. So all that's going to cancel all of that. Got to do it over here as well. And you can see that t is going to be equal to negative 12 divided by negative 2, which is positive 6. So we did that. All right. Not really anything new here, except this little bit of funny stuff with writing it as f of t. Okay. If we'd put r there, it would look just like what we did in the last chapter. Now, I got some functions here that are pretty common, and the picture stinks. All right. I'm not going to I stole these off somewhere off the internet. But this is a pretty good list of common functions. And if these things are going to be our friends, we ought to know them by sight, right? And kind of know what we're looking at and how they got the way that they are. Kind of like it's nice to know how your friends got the way they are. Right there, I'm going to draw over these blue lines because they're hard to see. It's still hard to see, isn't it? Okay. But if that is the function, notice that I'm always getting out the same thing. So this is what we call a constant function. And in this case, it looks like y is always equal to 2. So my function f of x is just 2. It never changes. Doesn't matter what x you put in there, you always get 2 out. So that's called a constant function. If you see a straight line running horizontal like that, you know you're dealing with a constant function. All you got to do is figure out where it crosses the y-axis and what's the y value of every one of those. Okay. This is called a linear function or an identity. Here it happens to be a perfect straight line. I'm going to put both of those down. Generally, I would call it a linear function because it makes a nice straight line. This one is a special case where if I put 1 in, I get 1 out. I put 2 in, I get 2 out. So the special case here would be the identity function, this particular one. Whereas, if this thing's sloped up like that or something, it would be a linear function, but not an identity function. So we'll try to just, leave both possibilities there. And okay, but that line is, and I'll do the linear function. Maybe that would make more sense if I did. Let me do that. Okay. Um, for the linear function, it's going to have a form where I have f of x, or I started to write y, but we'll do it in functional notation here. F of x equals some number. We called it m back in the last chapter, x plus b, where m was the slope and b was the y-intercept. For this particular one, this is an identity function where whatever I get in, it spits the same number right back out at me. And for that one, I would have f of x equals x. You can see how you could go from this top one right here. All we did was we said m was equal to 1 and b equals 0. Okay, and if that's true, then bam, I got myself an identity function and it would look like that. If it's some other numbers, then it's certainly still a linear function. You should recognize this one down here before we've come across this. This was our absolute function, absolute value function. And it's going to have some kind of form like f of x equals the absolute value of some stuff. Why did I do that? Um, and you could have a slope and here's the simplest version of it, and that indeed is what we're looking at there. It could have some other stuff scattered in there. So I'll include that. But the one that we're looking at there, where it comes down with a slope of 1, hits 0, bounces right back up, would be what we have here. It also could have some more stuff, maybe an ax plus b, might have some number out here plus c, something like that. Okay. If it's got absolute value, you're going to get that sharp angle in there where it bounces up. You can see why. Here I'm putting positive domain numbers in, putting positive x values, getting positive y, so it's going to go up. Back here, I put in negative x, and the absolute value makes them all positive. So that's what folds that thing back on itself right there and gives me that angle. Okay, we've seen this guy before. He's coming down, makes a nice bowl shaped right there. And that would be our friendly quadratic. We've talked about him. Of course, we know that you can factor, complete the square, or quadratic formula and, do a graphical thing. It's going to generally have a form y equals um, ax squared plus bx plus c. We're doing this in functional notation, so it'd be better to put f of x right there. But that is our quadratic. Right here, I have a curious one. It's coming down. It approaches 0, never really gets there. And this is what we call an inverse function, which has the form of f of x equals 1 over x. Okay? Think about putting x equals 1 in there. When I go 1 over 1, that would give me a 1, and I'd have a point. When I go up to 2, now I've got 1 over 2, which would be 1 half. 3 would be 1 over 3. And you can see how that's getting smaller and smaller, closer to 0. If I go all the way out to 10,000, now I'm at 1 over 10,000. Very small number, but it's still not 0, right? So I never really get down to 0. And as I get closer and closer to 0, I don't know, let's say we'll put a 0.25 in there. Well, 1 over 0.25, got decimals in a fraction. That's a big mess. But if I invert and multiply, then I'm going to get 4. And if I put, 0.1, I'd have 10. It's going to get bigger and bigger and here's kind of a branch point where calculus kind of begins. As we go this way and approach 0, my y value is approaching infinity up there. Okay, so that had a big deal to do with what Newton and the other guys did with calculus. Here's the other side of it right here. If I put in a negative number and invert it, then I'm going to have a negative number. It's going to have that same form. It's reflected across this line right there. It's just a mirror image of that. But that is the inverse function like that. This is called an inverse squared. And it looks a lot like the inverse. The main thing is that everything's positive. If I take positive numbers, put them in, I'm going to get a positive number. If I take negative numbers and square them, I'm going to get positive numbers. So the main thing it does is flip that up. It also makes it rise a little bit faster because now I'm squaring the numbers. But that's the characteristic behavior of an inverse squared function right there. All right. Three more here. Real quick, this is what y equals x cubed looks like. So I'll write f of x, the function of x, is equal to x cubed. Yeah, there could be some more numbers and fiddle with it and stuff, but that's a cubed function. This down here is a square root function. a squart. What am I writing? The square root function. There we go. And just think about some numbers we could put in here. Here's 0 right there, x equals 0. And the f of x of that square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. And so you can see some of those points there. Here's 4, goes up and touches right there. 1 is right there. And it's going to make that kind of flattened out curve as you go right there. This is a similar thing here, but this is actually a cube root function. And it's going to do a very similar thing on this side. Um, instead of squares, it's cubes, right? So if I take 0, then, here's x. I'm not saying x squared anymore. I'm actually saying x cubed here. So 0 times 0 times 0 is still 0, and we get the point 0, 0. 1 would still be 1, but 2, instead of being 1.414, it's now 8, right? So, oh, I got these backwards. I apologize. Look at me. Blah, blah, blah. Cube roots. Okay. So the form of this thing is f of x equals the cube root of x. So I actually need some numbers like 0 and 1 and 8. The cube root of 0 is 0. The cube root of 1 is 1. The cube root of 8 is 2. And so it's going to be a little bit flatter than that one up above. You can see it doesn't climb up as fast or as high in the limited range we've got there. The big difference is we also get the negative side. I cannot take negative numbers and get the square root of it, but I can get the cube root. Okay. And that's, I mentioned the word domain a while back. The elements of the domain would be anything that I can put into it. So the domain is only the positive numbers here, but the domain is all the numbers here. I have a bigger domain. I have a bigger set of things that I can throw in the top of that machine and turn the handle. And that's okay. Okay. I wanted to pull out the calculator here, and I've already made a big mess out of all this on the page, but just show you how easy it is to visualize and picture and graph some of these things with our modern technology. We'll hit y equals here. We've already done some of this. Here's a good one right here. We said this was the inverse function. So if I want to graph 1 over x, I just type 1 divided by x, and I hit graph. And it's going to draw that picture that we had right there. Okay, matching up with this guy. Okay, so any of these you could we'll do one more here. Let's do this cube root function down on the bottom. To get the cube root, you got to go math, step over using the right arrow key. And what just happened? Oh, I'm sorry, it is on the math. There it is. Okay, so there's my cube root function, and I'm just going to put in x, and I've already got an x in there, so let's kill that. And I graph, and here comes that curve that we had, down there on the bottom right. So real easy to graph these things on your calculator. It's kind of fun to play with them and see what happens, ooh, what would happen if I multiplied by a number in front of that? I'm going to leave the one I've got, and now let's put an 8 in front of that. So I'll hit 8 and math, go down and get the cube root, and then put in x, and hit graph. So there's the one that we had. Here comes the new one. You can see it's kind of the same shape, but it's bigger now. Everything's 8 times taller, right? So you can kind of play with that and see, what happens when I change these numbers? Can I make it stretch vertically? Can I stretch it horizontally? Can I shift it left or right, up or down? Well, yeah, that's real easy. If I wanted to shift this first one up 3 spaces, I could close the parenthesis and go +3. And part of what we want to do here is to think about that. And what does it take to move things? Where it did cross at 0, now it's You can see the whole thing's moved up 3 spaces. I didn't do anything to the second one, so it's still going to be the same. But it's good to start thinking about that. These are kind of maybe the 9 most common. These are our friends, and we kind of want to be able to see them and recognize them and go, oh yeah, you're a quadratic, you know. And if you see a problem on the piece of paper where it says 2x squared plus 4x plus 6, up, that's quadratic. It's going to make this little bowl shaped thing. Doesn't hurt to come in here and graph it. You can do that anytime you want. I don't remember what I said, 2x squared plus 4x plus 6, you know. But it's definitely going to have that bowl shape. And hmm, well, we're off the screen here. 2x squared plus 4x. Oh, I didn't get the x in there. That's the problem. Okay, yeah, that would do it. All right, so I'm going to insert an x, hit graph. This one ought to show. There we go. Okay, that makes sense. And see how it shoved the parabola up and to the left a little bit? We're going to talk about why that happens, but you can go ahead and start playing with that if you want and see what it does. Anyway, those ones are good to kind of know. Thought I deleted this. There are things that you can do other than numbers and still think about functions with. And I thought I'd gotten rid of this again, but if I take blue and I take yellow and I mix it. Uh-oh. Okay, I thought it was gonna it overcolored it. But there for a minute while I was doing it, maybe I'll try here again. You can see it. See how it makes it green right there? Blue plus yellow equals green. That's almost like a mathematical thing. I'm taking two elements. As soon as I turn loose of it, it just colors on top of it. But um, you can think about functions and adding elements of sets. Maybe it's color, maybe it's months of the year, maybe it's whatever's going on. But there are other things that we can think about in with functions too. Okay. Well, thanks for stopping by. That's today's little spiel, and bring your questions and let me know what I can do for you. Thanks. Have a good day.